Hello, boys and girls. I hope you're feeling happy and blessed. This lesson will be about tangent line approximation. What does that mean? Now, I hope you guys remember the tangent line problem. The question here is, if we have a function like f of x, how can we find the slope of the line that is tangent to it at some point, like p? So we want to find the slope of this line. Well, first of all, to find a slope, we need 2 points. And that's what made this question difficult, because we only had 1 point on f of x. However, we thought to ourselves, well, if we pick another point on f of x, let's call it q, and it's happening at some x value, drawing a line through p and q gives us a secant line. Remember, secant line means it intersects twice, as opposed to a tangent line which only intersects once, at one point. So we have this secant line PQ, and we can find its slope because now we have 2 points. Here, let me write some coordinates for P and Q. So we have that P is defined as the point x naught, comma y naught, and Q is defined as the point x, comma y. Okay, so the slope here would be the change in y's, or f of x minus f of x naught, all divided by, then change in x's, or x minus x naught. I would just like to add a little bit of notation here. It's useful to consider this distance between x and x naught as the change in x. Now, using this notation of change in x, we can rewrite the slope of the secant line, the slope of PQ, as, instead of writing x minus x naught in the denominator, we can just write change in x. And the y values in the numerator, we can also write them differently. Notice that x is equal to x naught plus the change in x, right? If we add this value, x naught, plus this distance, which is change in x, then we would get this value, x. Using that, instead of x, we can write f of x naught plus the change in x minus f of x naught. Here's a little visual so we can notice how the secant line behaves as we pull Q closer and closer to P. And here's where we can introduce the concept of limits. The limit as the change in x approaches 0. So what we're doing is taking this distance and making it smaller and smaller, or closer and closer to 0, right? So as this value, the change in x, gets closer to 0, the slope of the secant line, the slope of PQ, or f of x naught plus the change in x minus f of x naught, all divided by the change in x, gets closer and closer, or equals the slope of the tangent line. And we came up with a notation for that, right? F prime of x. We can also write a shorthand version of this. The limit as the change in x approaches 0 of, in the numerator we'll write change in y over change in x. And from the previous equation, we can see that that is also another way of writing the limit definition of a derivative. Having this understanding and of the slope of the tangent line and how it's related to derivatives will be useful in learning this lesson's topic, which is the tangent line approximation, or linear approximation. Now, we're also used to seeing this notation dy dx as being the derivative, right? Well, let's be clear about a few things. There's a difference between the change in x, the change in y, and dx and dy. And we'll use the picture here to make sense of these differences. Thinking about the points P and Q, we have the change in x, which is the distance in their x values, or the change in the x values. We get this by subtracting x minus x naught. The change in y then would be the difference between the y values of P and Q. So we would get that by subtracting the y value of Q, which is f of x, minus the y value of P, which is f of x naught. Dx, on the other hand, well, dx and dy both have to do with the slope of the tangent line. They don't have anything to do with the point Q necessarily. So dx would be this distance here. Okay, so that would be the distance from P to N, which we can find by subtracting the x values, x minus x naught, which, notice, is the same thing as delta x, or the change in x. Now let's see about dy. dy would be this distance here, or the distance between the points M and N. And this is based off what we know about slopes. So remember here, slopes our rise over run. In this case, dx would be our run and dy would be our rise. Now we can take this equation, dy dx equals f prime of x, and in it we can solve for dy. And we'll do so by multiplying both sides by dx, so we get dy equals f prime of x times dx. And we can add some vocabulary now. The differential of x is our dx, which is the same thing as the change in x, as we saw from the graph, which cannot be 0. The differential of y is defined as dy, which, according to the equation that we just found up here, is equal to f prime of x times dx. Okay, so we have for f of x equals x times e to the x, find the differential of y. Okay, so we know that dy is equal to f prime of x times dx. This is the definition. We can take the derivative of f of x, which we have up here. Notice that we need to use product rule here. We have the product of two functions, x times an exponential function, so polynomial times an exponential function. We would have x times the derivative of e to the x, which is e to the x, plus e to the x times the derivative of x, which is 1. And I'll write the 1 there just to be safe. All of this times dx. I'm going to simplify this a bit. We can pull out the common factor, which is e to the x. So we have e to the x times x plus 1 dx. And that's our differential of y or dy. Okay, so moving on to our next question. Compare dy to the change in y when x equals 0 and the change in x is 0.5. We'll start with dy, or the differential of y, which we just found the equation to way up here. Okay, so notice what we're plugging in is 0 for x and 0.5 for dx. Remember, dx, or the differential of x, is the same as the change in x, as we saw in our graph. We have e to the 0 times 0 plus 1 times 0.5, which gives us 1 times 0.5, or 0.5. Now, the question is asking us to compare that to the actual change in y. To find the actual change in y, we subtract the y values, right? So we would subtract f of 0.5 minus f of 0. We'd have to look at our equation up here, the original. We're plugging in, so we have 0.5 times e to the 0.5 minus 0, which gives us 0.824. Now, if we compare these two values, they're not quite that close to each other, right? There's a little bit of a margin of error here. So let's see what happens when we make our delta x a little bit smaller. We'll start again with dy. So dy is equal to, notice we're plugging in 0 for x and 0.1 for dx. So we have dy is equal to e to the 0 times 0 plus 1 times 0.1, or 0.1. If we look for our actual change in y, we'd plug in f of 0.1 minus f of 0, which gives us 0.1 times e to 0.1, we're plugging into the original, minus 0, which is 0.111. Look at this. If we compare these two values, they are way closer than what we had previously. Let's see what happens when we make our change in x even smaller, even closer to 0. So our dy would be dy is equal to e to the 0 times 0 plus 1 times 0.01, which gives us 0.01. Our actual change in y would be f of 0.01 minus f of 0, which is 0.01 e to the 0.01 power minus 0, and that gives us 0.010. Now look how close these are. Notice that with the previous two answers, if we were to round our change in y's to the nearest tenth or to the nearest hundredth, we would have the same answers for dy and the change in y. If we look back at our previous three examples, notice that the closer and closer the change in x, or delta x, gets to 0, then dy and the change in y get closer and closer to each other as well. So we have that as delta x approaches 0, then dy, the differential of y, approaches the actual change in y. If we look at our graph, what this means is that as delta x gets smaller and smaller, so as this distance gets smaller and smaller, or as this point approaches p, then this distance, dy, gets closer and closer to this distance, the change in y. As we bring x closer to x naught, this distance will be closer into this one, as we can see by these drawings here. Now from these observations we can come up with something really cool. Since we have that the differential of y, or dy, is getting closer and closer to the actual change in y, we can say that dy is approximately equal to the change in y. Well, dy, remember we came up with an equation for it way at the beginning of this lesson. Dy is the same thing as f prime of x times dx. And the change in y, well, we get that by subtracting the y values. So that'd be f of x minus f of x naught. Now let's be careful with our notation here, because really remember that the dy and dx that we're talking about is very specific to the point P. So we're talking about the slope of the tangent line at P, meaning this f prime of x is not so much a function as it is an actual value. So this is f prime of x naught, or the derivative of f of x at the point x naught. From here, notice that we have f of x in this equation, our original, so we'll solve for it by adding f of x naught to both sides, and we have f of x is approximately f of x naught plus f prime of x naught times dx. And that brings us to our theorem. The linear approximation L of x to a differentiable function f at x equals x naught is given by, and we just derived the equation ourselves up there. So L of x is equal to f of x naught plus f prime of x naught times dx. But wait a second, we can write this even better. Remember, dx is the same as your change in x, and we can find the change in x by subtracting the x values, so that'd be x minus x naught. And our final equation looks like this. Now I want us to look at this graph here, and I want us to notice something. A while ago we said that as delta x approaches 0, dy approaches the change in y. So we have that as this distance gets smaller and smaller, meaning this point gets closer and closer to this point. Notice what's happening to the gap between the tangent line and the function itself. So we want to keep an eye on this distance here. Notice here, once the point is a little bit closer, our gap is way smaller. And here, once our point is this close, our gap seems to be almost non-existent. So as delta x gets smaller, the closer the tangent line is to the graph. This is why we can use the tangent line to f at P as a linear approximation to f near P, this being our point P. So again, what we're doing is we're taking this line, this tangent line, and we're using it to approximate y values on the original curve. Notice that the closer the y values are to this point P, then the more accurate our approximation will be. Let's answer our second question. Find L of x, linear approximation to f of x equals sine of x near x equals 0. So we just found that the linear approximation L of x is equal to f of x naught plus f prime of x naught times x minus x naught. The way the question is phrased is that they're asking us to find the linear approximation near x equals 0, so that would be our x naught. And we have that L of x is equal to f of 0 plus f prime of 0 times x minus 0, which gives us sine of 0 plus the derivative of sine of x, so that's cosine, plug in 0, times x, which gives us 0 plus 1 times x, or x. So our linear approximation to f of x equals sine of x near x equals 0 is x. Let's see what happens if we put both of these functions on a graph. So this is what we have when we graph L of x and f of x. Remember, L of x is the linear approximation, or our linear estimate of f of x. And if you look at this window between, that seems to be negative 0.5 and 0.5, if we look at this window, it seems that L of x and f of x are actually one on top of the other, meaning that using this equation to approximate the y values of f of x in this interval, we would get a pretty accurate answer. Let's put the numbers to the test. We're going to compare our values for L of x and f of x to see how accurate our linear approximation really is. L of negative 0.3 would give us negative 0.3. Remember, L of x is x and f of x is just sine of x. Okay, so f of negative 0.3 would be sine of negative 0.3, which gives us negative 0.295 if we truncate after 3 decimals, like the AP exam likes us to do. Now, L of 0.1 would just be 0.1, and f of 0.1 would give us sine of 0.1. We put that in a calculator and we get 0.099. Finally, we have sine of pi over 4. That's what we want to approximate. So L of pi over 4 would be just pi over 4, which is approximately 0.785 if we truncate. And now f of pi over 4, which is sine of pi over 4, which we know is square root of 2 over 2, which is approximately 0.707. Let's look at the numbers that we just calculated. For negative 0.3, we got negative 0.3 as the estimate and negative 0.295 as the actual value. If you notice, if we were to round the actual value to the nearest tenth instead, then our approximation would be exact. Let's look at the next one, 0.1 and 0.099. Notice if we were to round once again to the nearest tenth, we would have the same value in our approximation L of x and our actual y value f of x. Now for pi over 4, there's a little bit of a larger difference, but still small enough to ignore. And notice that the most accurate answers are between that window that we noticed from the graph, which was between negative half and half, where the two functions L of x and f of x seem to coincide. Let's look at that one more time. Remember, this piece of graph right here seems to have both functions, one on top of the other, and that's from negative half to half. And that's where our approximation would be the most accurate, as we can see when we work out the numbers. Here's our third question. A spherical bearing has a radius of 3 centimeters when it's new. Use differentials to approximate the volume of the metal lost after the bearing wears down to a radius of 2.971 centimeters. Find the actual volume and compare the approximation to the actual volume lost. Okay, so we have a sphere and it's shrinking, right? It has this radius r and the sphere is shrinking. So we want to use differentials to approximate the volume that was lost. In this case, our original radius or initial radius is 3 centimeters. And we want to approximate the new volume once the radius is 2.971 centimeters. Okay, so we want to know what is the change in volume. Well, in this case, dr, or the change in r, would be 2.971 minus 3, which gives us negative 0.029. And this is a value that is very, very close to 0. So we should be able to use differentials to get a pretty close approximation. Since our change in r is very close to 0, then we expect our actual change in volume to be approximately our dv, or differential of v, which would be v of r naught times dr. And that's going back to the equation that we derived way in the beginning of the lesson. Now we have to remember that the volume of a sphere is 4 over 3 pi r cubed, meaning the derivative, or v prime, would be 3 times 4 over 3 pi r squared, where the 3's will cancel. So going back to our equation over here, we have 4 pi r naught squared times dr, which gives us 4 pi times 3 squared times negative 0.029, which once we put that in the calculator gives us negative 3.280 if we round it to the nearest thousandths. That is our approximation. And we would say there was a loss of approximately 3.280 cubic centimeters. Remember, we're talking about a volume here. And notice that we don't say that the volume is negative. Instead, we account for that negative by using the word loss. Now, remember that they also asked us to compare our estimation or our approximation to the actual volume that was lost. So now we want to find the actual change in V. Well, that would be V of R minus V of R naught, or the volume when the radius has already shrunk to 2.971 centimeters minus the volume in its original shape. So we would have 4 over 3 pi times 2.971 cubed minus 4 over 3 pi times 3 cubed, or 27. We put all of this mumbo jumbo into the calculator and we get another negative number, negative 3.248. So that's our actual loss in volume. We could say there was an actual loss in volume of the bearing of 3.248, don't forget the units, cubic centimeters. And since they want a comparison, what we could say is that our approximation was actually an over approximation. So we could say that the differentials in this case yield an over approximation of, and to figure this number out, we would just have to subtract, right? So we have 3.28 minus 3.248, so our approximation minus our actual value. We put that in the calculator and that gives us 0.032. The units here would also be cubic centimeters. And there you have it. So remember, this topic is called the tangent line approximation, right? And what we're doing is using our tangent line at a point to approximate y values on the curve. If you notice, in our previous question, we got an over approximation, which kind of makes you think that we can also have under approximations sometimes. And if we look at the very first question we did, our dy, our differential of y, gave us under approximations. So let's look at these two pictures to see if we can figure out when each case is happening, when we're getting an over approximation and when we're getting an under approximation. Now, if we look at graph A, we see that there's a tangent line drawn through point P and it is below g of x. If we look at graph B, we have the curve h of x and a tangent line through the point Q that is on h of x. In this case, the tangent line is on top of our curve. So for graph A, our tangent line approximation would give us an under approximation, simply because the y values on the line will be smaller or below or lower than the y values on g of x. In graph B, our tangent line will give us an over approximation because the points on the tangent line, those y values will be greater than the points on the curve, the y values on the curve. Now, I hope you're noticing the key difference between g of x and h of x, and it has to do with their concavity. So notice g of x is concave up, so the tangent line is below it, and h of x is concave down, so its tangent line is above it. Let's focus on graph A for a little bit, and let's tie this picture back to our lesson. So remember the equation that we found a long time ago in our theorem, L of x, the linear approximation? Well, that would be the equation to this tangent line. And remember, L of x is equal to f of x naught plus f prime of x naught times dx, or x minus x naught, that being our change in x, which is equal to our differential of x. Now, I want us to realize that this equation is not absolutely new to us. In fact, notice what we have here. L of x, this is really meant to be the point on our function. And before I go further, let me actually just tie these letters to our graph all the way. We should actually have L of x is equal to g of x naught plus g prime of x naught times x minus x naught. So now our equation matches our picture entirely because our function in the picture is called g of x. Now what I was saying was, this L of x, really what it stands for is for the y value on the function g of x. So we have g of x is equal to g of x naught plus g prime of x naught times x minus x naught. And if we move this guy over here, we have g of x minus g of x naught equals g prime of x naught times x minus x naught, right? Now, wait a second, these are just y values. And these are just x values. So we have g of x could be y2, g prime of x naught could be y1. Then we have their corresponding x values. X would be x2 and x naught would be x1. If we replace that into our equation, what we really have is y2 minus y1 equals g prime of x naught times x2 minus x1. And also remember that this just means the slope of the tangent line to g of x at x equals x naught, at the point x naught. So that's just a slope, right? We can say that that's m, we can call it m. And taking a look at our equation, we have y2 minus y1 equals m times x2 minus x1. And that should look absolutely familiar to you guys here. That's just our point slope formula. Now, isn't that cool? Well, that wraps up our lesson on local linearity, which is just another fancy term for linear approximation or tangent line approximation. I hope that was helpful. Stay bright. Remember, you can do anything you put your mind to.